Hello, and welcome to Swecodes. In this lesson, we will solve a small but very useful problem that teaches careful thinking and clean coding. Two people start at different positions on a straight number line, and a friend is waiting at a fixed position. Both people move toward the friend at exactly the same speed. Our task is to decide which person reaches the friend first, or whether they arrive at the same time. We are given three integers. X is the position of person 1, Y is the position of person 2, and Z is the position of the friend who does not move. If person 1 arrives first, we must return 1. If person 2 arrives first, we must return 2, and if both arrive at the same time, we must return 0. Because both people move at the same speed, the arrival time depends only on how far each person is from Z. The distance from x to z is the absolute value of z minus x, and the distance from y to z is the absolute value of z minus y. If the first distance is smaller than the second, the answer is 1. If the second distance is smaller than the first, the answer is 2. And if the two distances are equal, the answer is 0. All three numbers, x, y, and z, are integers between 1 and 100, which means the inputs are small and easy to work with. The movement happens on a one-dimensional number line, so we only think about forward and backward along a straight path. The speeds are equal, which is the crucial hint that lets us compare distances directly instead of simulating time. Since time equals distance divided by speed, and the speeds match, comparing times is exactly the same as comparing distances. To understand the idea, imagine the three marks on a number line. One mark at x for person 1, one mark at y for person 2, and one mark at z for the friend. The winner is simply the person whose starting mark is closer to z, and if both marks are equally far from z, then both people arrive at the same time, and the result is a tie. In the first example, the distance from person 1 to the friend is 4 minus 2, which equals 2. And the distance from person 2 to the friend is 4 minus 7, which equals 3. Since both move at the same speed, and person 1 has the shorter distance to cover, person 1 arrives first, and the correct answer is 1. In the second example, the distance from person 1 to the friend is 6 minus 2, which equals 4, and the distance from person 2 to the friend is 6 minus 5, which equals 1. Because person 2 is closer to the friend, person 2 arrives first, and the correct answer is 1, 2. In the third example, the distance from person 1 to the friend is the absolute value of 3 minus 1, which equals 2, and the distance from person 2 to the friend is the absolute value of 3 minus 1, which equals 2. 2 to the friend is the absolute value of 3 minus 5, which also equals 2. Since both distances are the same, both people arrive at the same time, and the correct answer is 0. A simple plan helps you solve this reliably every time. First, restate the decision we must make. Return 1, 2, or 0. Second, translate the story into numbers by computing the absolute distances to z for person 1 and person 2. Third, compare the two distances and decide the result. Finally, sanity check your decision with the examples and remember to include the tie case and the case where someone is already standing at z. The first approach is to simulate the race step by step. At each step in time, you move person 1 by 1 unit towards z and move person 2 by 1 unit towards z. After each step, you check whether both have reached z at the same time, which means you return 0. Otherwise, you check whether person 1 has reached z first, which means you return 1, and if not, you check whether person 2 has reached z first, which means you return 2. This approach matches the story closely and builds strong intuition, but it does more work than necessary because you can decide the answer by comparing distances directly. The second approach is the clean and optimal solution. You compute a as the absolute value of z minus x and b as the absolute value of z minus y. If a and b are equal, you return 0. If a is less than b, you return 1, and if a is greater than b, you return 2. This approach runs in constant time and constant space and expresses the heart of the problem very clearly. The third approach organizes the same idea in a way that scales easily. You place both distances into a small array or list. Check whether the two values are equal to handle the tie, and otherwise pick the smaller value and map it back to the correct person. This pattern is helpful if the problem later extends to more than two people because you can compute all distances, select the smallest, and manage ties in a consistent way. You can think of the two distances as two horizontal bars that represent how much ground each person needs to cover. The shorter bar represents the person who will arrive first because, with equal speeds, a smaller distance always leads to a smaller time.
The brute force simulation can take as many steps as the total distance the two people need to cover, so its running time is proportional to the sum of their distances to z, and its space usage is constant. The direct comparison and the vectorized minimum approach both run in constant time and use constant space because they only compute a couple of absolute values and perform a few comparisons. In Java, you keep two variables p1 and p2 that start at x and y. In a loop, you move p1 1 unit closer to z, and you move p2 1 unit closer to z. After the movement, you check in this order. If both p1 and p2 equal z, you return 0 to indicate a tie. If only p1 equals z, you return 1, and if only p2 equals z, you return 2. This code mirrors the story and is good practice for loops and conditional checks. In Python, you follow the same steps with concise syntax. You store p1 and p2, move each 1 unit toward z in a loop, and after each update you check first for the tie, then for person 1 winning, and then for person 2 winning. The logic matches the Java version and is easy to read and test. In Java, the optimal code is short and direct. You compute as math.abs z-x and b as math.abs z-y. If it equals b, you return 0. If it is less than b, you return 1, and otherwise you return 2. This code expresses the solution exactly and avoids extra work. In Python, you compute as abs z-x and b as abs z-y. If it equals b, you return 0. If it is less than b, you return 1, and otherwise you return 2. This version is straightforward and very readable, which makes it ideal for interviews and practice. In Java, the vectorized version places both distances into an array, checks whether they are equal to handle the tie case, and otherwise returns the correct person by comparing the two entries. This structure makes it easy to extend the solution if more participants are added later. In Python, you store the two distances in a list, check whether the two values are equal to handle the tie, and otherwise return 1 if the first distance is smaller or 2 if the second distance is smaller. This pattern is short, clear, and easy to scale. The most important lesson is that equal speeds make distance the only factor that decides who arrives first. You compute the absolute distances z-x and z-y, and you return 1 if person 1 is closer. You return 2 if person 2 is closer, and you return 0 if they are equally far. You can use the simulation to build understanding, the direct comparison to solve quickly and clearly, and the vectorized style to prepare for versions of the problem with more people. Thoughtful, you have taken a short story and turned it into exact logic and clean code in both Java and Python. If you keep practicing this way, by translating words into simple math and then into code, you will find that many problems become easier. You will find that many problems become easier. Thank you for watching Swecodes, and I hope to see you in the next session where we will keep building your problem-solving skills step by step.